Now the IP layer. The IP layer was really the invention of the internet. It was done in 1979, if I'm correct. The very first internet, which was called DARPANET, was using store and forward. So all first instantiations of computer networking use that principle of store and forward. And then the major breakthrough was the separation of the invention of packet switching, or the adoption of packet switching. There were other networks that were doing packet switching, and the invention of IP and TCP that before were like one bundle. The design principles that were done at that time are still those that govern the internet today. The good news is that there are very few design principles. The bad news is that there are many ways that those design principles have been violated. One of them, which is dominant and visible everywhere today, is called the network address translation box that we will discuss in a few more minutes. And this is very typical of the internet. I mean, or computer systems in general. Computer systems are the result of an evolution done by human beings, by smart human beings, but still human beings. So they do things like nature. In some sense, they do things when it's needed, and then only after we try to make a big intelligent story about it. Still, it is considerably less complicated than nature because the systems have been designed very, very recently, so there's much less complexity. And this complexity can even be further reduced if we separate the principles from the violations. Instead of saying, here is how things are done, it's much easier to understand why they are the way they are if we think that at the beginning, people have arranged things in some way, and then they found that there are a few problems on the corner that if you tweak a bit the principle, it still works, so why not do it? So this is exactly what we will try to do. So first I will go through the principle, and in 15 slides I will go through the violations. The first principle is longest prefix match. The IP addresses are meant to be topological, structured. They reflect an organization of the internet. Every interface has an IP address. If you use TCP-IP, you have to have IP addresses, even if you don't need them. For example, if two systems are in the same local area network, they could communicate without IP addresses. But the principle of TCP/IP is, even if they could, you should not do it. So you should use IP addresses. By the way, that's a principle that has not been violated very much. Then every system must have a forwarding table, which is often called a routing table, that says what we should do in order to reach various destinations. We say every system, but in practice, the routing table is minuscule or quasi-empty in end systems, in hosts, and is very big in routers. But in the internet, hosts and routers are built according to the same principles. Here is an illustration of this principle. I'm showing three machines, Lisa on the left, Bart and Homer on the right. Lisa is sending a packet to Bart and Homer, and their addresses are b.d.h2. Those are symbolic notations. The IP addresses we've seen are not like this. They are not variable size. They are 128, 178. They're all the same size. But here I'm making the story a bit simpler. I assume that we can recognize different prefixes. So think of B as a string of bits, D a string of bits, and H2 also a string of bits, such that the total length is the correct length for the given version of IP that we're using. If this is IPv4, in total there should be 32 bits. If it's IPv6, in total there should be 128. But we can arrange them as sub-blocks. When Lisa sends a packet to Homer, the packet has destination address b.c.h2, and then the routers on the way must analyze what to do with the packet. So they must have a routing table, and the story says we should do longest prefix match. That means when the packet reaches router R1, it tries to find in the table a match. So the table has things like A dot star means A and then whatever comes after A. And B dot star, the destination address matches the first line, B dot star does not match the second, so we have no choice, we use the first line, and it says the output is 2. Output 2 is, for example, on the computers we use in the labs, that would be the name of an interface like ETH0, ETH1, ETH2, etc. So the packet goes via interface number 2, which means it will reach router R2. In reality, you may need more information. You may need a MAC address if you use Ethernet to reach router R2, but we'll come to these details a bit later. At router R2, the packet arrives and has to match the entries in the table. Now there are 2 entries in the table that match. The third and the second, B.D and B. Both match. Now we take the longest prefix. The longest prefix is B.D. So we choose the one that has the longest prefix, which means the most specific. So it will go to output number, sorry, this is B.C. I said something wrong, I pull back, It doesn't match B.D, it matches only B. There is a single match, and then it goes to port number 3, etc., similar at router R3. The thing becomes more interesting when we talk of the packet that goes to BART, B.D.H2, and then the difference is at router number 2, where this red packet matches 2 entries, and we will use the more specific one. So we should interpret this routing table by saying, at router 2, by saying anything that starts with B, except B.D, should go to number 3. But we don't have to say the except. We write one line, and if we don't write more specific lines, this line we'll use, if there are more specific lines, they come as exception. That's the first principle of the IP layer, and this is used to do things like aggregation and default routes. With this principle, for example, an IP router of EPFL that is not at the border of EPFL, but that's in the middle of EPFL, can have one route that says everything that is not an EPFL address is outside, therefore should go to the routers that are an interface between EPFL and the rest of the world. So it could, and because this is for anything other than the EPFL addresses, that means such a router can simply have routing table entries for only the EPFL prefixes. And then anything that does not match the EPFL prefixes, we can have only one route that matches nothing, an empty string, and this is called the default route. So this is a very powerful mechanism that we will use repeatedly in the lab and others to compress the routing tables. That's the first principle of IP. The second principle is don't use routers inside a LAN. So if B and E communicate with each other, so if you have a peer-to-peer application that goes from a mobile to a desktop, for example, that may be Dropbox if you have enabled local synchronization. Then the principle says packets from B to E should not go through the router. The router should not see them, should not forward them. They should go directly through the Wi-Fi base stations, which makes sense because the Wi-Fi base station is there to unite all the systems together. This principle is inherited from the past. It's a bit strange today in some sense, but it comes from the fact that IP, as the name stands, is not networking, but is inter-networking. The I stands for inter-network protocol. When IP was created, the networks were the MAC layer networks in the 70s and the beginning of the 80s. There were MAC layer networks in the Microsoft world for interconnecting a printer and a PC. There were similar networks in the IBM world, in the DEC world, etc. They all had their own networking infrastructure. Apple also had AppleTalk, that was a networking of its own. Some of those networks were pure MAC layer networks. Some of other networks had their own fancy addressing schemes. And IP was conceived as a mechanism to interconnect all those things together. You wanted to interconnect a Windows PC to an Apple Macintosh, then the only way was to use IP for that. So it was an inter-networking technology. And we find a reflection of this in this principle, that IP views the world as an interconnection of networks that today are local area networks that use MAC layer to communicate with each other. And in particular, if two systems are on the same MAC layer network, which in IP terminology is called a subnet, then they should not go through a router. And this is why we have subnet masks, because we need a way when B sends a packet to E, it needs to know whether it should send it directly to E, which concretely means whether it should find the MAC address of E and create an Ethernet packet or a Wi-Fi packet with MAC destination address E, or whether it should go via a router, in which case the MAC address it should use is the MAC address of the router. So it should be visible to the hosts. Voilà, merci. So, equipped with that, here is one more quiz. We observe a packet from W to P to the printer at the observation 1. Which destination address do we see at the IP layer? I close in 5 seconds. I try to close, yes. And the correct answer is A. I could also see the evolution of your answers. So it started with a majority of C, then it changed and converged to a majority of A, which is the correct answer. So be careful here, there is an apparent paradox. You should not confuse two things. Communication between two end systems that are in the same subnet goes directly using only the MAC layer mechanisms, but it is still an IP communication. You still send IP packets. You don't change the format, you don't decide, I send an IP header or I don't send it depending on the destination. No, you don't do that. You always create an IP packet header, and then you let something decide whether you send it via Ethernet to the router or to the end system. That's how it works today. A bit more of terminology. We've seen an IP data unit, protocol data unit is a packet. An intermediate system is called a router. So by definition, an intermediate system of any interaction is something that is in the middle. That means that it is not the source and not the destination. An IP system that is not an intermediate system is called a host. Routers in the very early days of the internet were called gateways. That's another term that was used for intermediate system. Today, gateway tends to mean an intermediate system of the application layer, which in principle should not exist because we don't do store and forward, but as we will see, sometimes we do use intermediate systems of the application layer. But we will find that in the documentation. If you go to the documentation of many operating systems, it will ask for what is the default gateway, which means what is the default router of an interface. A few words about addresses. We've started saying that already. If you're not familiar with binary and hexadecimal, then it's the time to become familiar. If you are, it will be easy. IP addresses of the format IPv4 are 32 bits. They are written by groups of 8 bits in decimal notation, which is a very cumbersome thing, but it's done because when this was invented, people were not familiar with hexadecimal digits. We can and we will sometime write them using hexadecimal digit. So, for example, the 128.191.151.1 address is 80BF9701 in hexadecimal. And if you want to write it in binary, which we normally don't do, but mentally it's a good idea to be able to do it, this is what we would have. So 2 is this, so 0, 1 hexadecimal digit is 4 bits, and we write them in base 2. So this is the number 2 in binary, 0 plus 1 times 2, this is part 4, 8, 16, etc. Numbers to remember is all 1 binary is FF, because F, the number F, which is the last digit in the hexadecimal system, which is the number 15, corresponds to 4 bits, equal to 1. And if you do it twice, that gives 255. Every time it is 2, so 4 times 4 bits equal to 1 is 2 to the power 4 minus 1. Because if I add 1 to this, I will have a carry 4 times. I will have 1 followed by 4 zeros, which is 2 to the power 4. So it is 2 to the power 4, 16, minus 1, 15. And the same for this one, 2 to the power 8, which is 255, 56, minus 1, 255. Those are numbers that we will see all the time. We will see them in masks. For example, we've seen last week that a subnet mask equal to 255, 255, 255. That means that we have 3 times a block of 8 bits equal to 1, which is a cumbersome way of saying that the prefix is 16 bits. Here is a simplified version of a fraction of the EPFL network. Local area networks are indicated by shared lines. In fact, they represent switches, typically. And you recognize perhaps something. All EPFL addresses have something in common. They start with 128.178. Here I'm not showing some other addresses that are 128.179, which means that the prefix that is shared by all EPFL addresses is how many bits? 16 if it would be 128.178, but since we also allow 128.179, the difference between 128 and 178, between 178 and 179, if you have a calculator on your smartphone and write it in binary, you will see the difference is only the last bit, which is 0 or 1. So in fact, the prefix here is 15 bits. The first 15 bits prefix uniquely identifies EPFL in the world. That's one of the principles of IP. The prefix corresponds to a location in the internet. Now, is it a good idea to have a prefix for EPFL? Well, when the IP was created, it was a network of universities, and EPFL was one of the very early adopters of TCP-IP. Therefore, it was one of the big nodes, so it had a prefix for itself. Today, EPFL is a minuscule fraction of the internet, so it should not probably have such a large prefix. And we'll see that for IPv6, this is what happens. Network prefixes are used in routing tables. In the simplified figure I showed 10 minutes ago, I had things like A.B.*. This is not how we see things when we will play in the lab. We will see things like the prefix is 128.168/16. The slash means the first 16 bits of whatever is before. So here is, for example, the routing table at the node that is circled in red. It has two entries, 128.168/178/16, with the next hop, which is the router that is just below, and another destination, which is 0.0. What do those two lines mean? Well, it means that whenever this router receives a packet, it will do a match in the table. And the table is not long, so either the first line matches, which means it is a packet that belongs to EPFL, and is the 128.179 is used for wireless or weird things. So the main wired network of EPFL is 128.178. That means it is a packet that must go to the rest to the EPFL. And since this network is connected to only one other router to the rest of EPFL, there's only one way it can go to the rest of EPFL. So it has only one line. Now, if this router receives a packet to another address that is at IBM 9. something or at ETH 129.132. something, it will match only the second table, the second line, which is an empty line, 0 bits, which means it matches everything. That's the universal match. This is what I called earlier a default route. Any packet that matches this will go to 130.59.22.2, which is a router inside the switch backbone, the backbone of the internet service provider that connects EPFL to the rest of the world. If I take another router that is more in the middle of EPFL, we will find the same two things. One default route for the rest of EPFL, which points to the router that is upstream in the hierarchy of routers, because EPFL is built as a hierarchy. You don't have to build a hierarchy in an internet network, but typically you do. So you have the concept of a backbone and border routers. So this router is not in the backbone, and whenever it has something to say, it will send it to the red router, which is now on the backbone. And no, sorry, it will send it to another router that is on the backbone. And it has also a specific route which corresponds to another local area network that is connected to it on some of its other ports. So this is a typical use of routing table, I would say, in a well-structured network. If you have a network that is not well-structured, you may have a very long routing table. If it's well-structured, you can compress it dramatically. Routers that are at the core of the internet, like the routers of the France Telecom backbone, of the AT&T backbone, they have a very, very large routing table because they don't have default routes. They are the center of the internet, so they don't have, if it doesn't match, go to somewhere else. At EPFL, we do that. When you're in the core of the internet, you don't do that. The number of routing table entries that we have in one core router today is order of 500,000. That's the size of the number of tables today. With IPv4. With IPv6, it is much less. IPv4 is not so well structured, so even though we have a principle of topological aggregation, with IPv4, it is not easy to do. Not easy to do because networks like EPFL, for example, have a higher level prefix, which does not make sense. We are not at the core of the internet. The system managers of EPFL are not in the business of providing worldwide internet service for everyone. They're just serving a campus. We are served by an internet service provider, which is called Switch, which doesn't either have as principle to serve as a backbone provider for the world. So Switch is itself connected to backbone providers. So we should see that in the addresses, but we don't for IPv4. We will see that we do see it for IPv6. So for IPv4, the level of aggregation is not very large. There are special addresses that are very important to know because we will be confronted with them very, very frequently. The 127.0.0.1, which means this host. It's called the loopback address. It's a special address that is used for various purposes. For example, for debugging, when you are testing a program, you don't want to send it on the internet, but you want to send it to another machine and to another process on your machine that later will be migrated to another machine. Then you send it to yourself. Of course, if you send to yourself, you could send by direct inter-process communication mechanisms that don't use IP addresses, but you can use IP addresses to send to another process. The benefit of doing that is that if the other process is no longer on the same machine, you don't need to change your program, you just need to change the destination address. There's a whole block of 24 bits for that, but as far as I know, there's only one of those addresses that's used most of the time, which is the one address in that block. Then there are other addresses that you probably have seen a lot that are the so-called private addresses. There are three blocks, a block of 8-bit prefix, the 10 block, the 172.16 of 12 bits, so the first 12 bits of this, and the 192.168. Those four blocks are private addresses. Those are addresses that are, you can do with them whatever you want. I mean, the EPFL addresses are given to EPFL. If someone else in the world takes it, that will create trouble, and the EPFL could complain to the internet service providers that's using those addresses. The internet service provider is not allowed to reuse addresses that are not allocated, except the private addresses. Everybody can use them. You can, at home, build a network with 1 million computers, use addresses that are in the block 10, and as long as your network is private, does not go into the internet, that's perfectly legal, nobody will complain. In fact, most of the computers today use 10-something addresses. All the computers that are, perhaps not most, but most computers that are used by companies use 10-something address. If you're Nestle or UBS, you have a huge number of computers that are not visible to the outside world, that are in your private intranet, and for them you don't need special addresses, you just use the 10-dot addresses. Of course, in principle, those computers cannot communicate with the outside world, at least not using the IP layer. We will see that they can using a trick called the NAT. At home, if you have ADSL, you probably have a 192.168.something address. There is another type of address which is practically the same, which is called LinkLocal. LinkLocal means local to a local area network. Link means the same as LAN, means the same as MAC. So a LinkLocal address means that's an address that you're allowed to use only for communicating between two systems that are on the same LAN. That's a bit weird. Why would you care about that? Well, you care about that when you try to connect. I mean, typically when your Mac or PC boots at home, it will send a discovery message called DHCP to discover whether there is a router. In principle, you have a router at home that performs an additional function in addition to router, which is called address allocation. It will allocate to your PC an address. You can also manually give whatever address you want, but if you tick the box automatically assign address, it will be given by your router that will probably, if it's a small scale router, will give an address 192.168 dot something. If there is no router, if you connect a PC to a printer, for example, in the old days they would use NetBIOS or AppleTalk, but if they use TCP-IP, which is in principle what everybody does today, they will still need IP addresses to communicate. That's what we've illustrated in a quiz a few minutes ago. But nobody gives them an address. So they will give an address, and the question is, what should the prefix be? Well, the prefix is something that can exist only in a routerless world, and that comes from this subnet here. So such a subnet, this 16 block, in principle, in practice you can always cheat, as we will see a number of examples, but in principle that means that's a big block where everything is interconnected at the MAC layer. You can build networks at the MAC layer up to a few thousand hosts if you work hard. If you don't work hard, probably up to 100 hosts. If you go beyond that, then it would not work. There are special addresses that are used for multicast. Multicast addresses are very special. They have nothing to do with all the principle we've seen, so we'll talk about them again. With multicast addresses, the address is not the address of a machine, but is a logical address, is the address of a group. It's like a TV channel or a radio channel. If you send to a given multicast address, you don't know to whom you're sending. You're just sending to a group. And anybody who wants to receive needs to subscribe to this address and will receive the data. We'll talk more about multicast a bit later. Multicast was meant to be used for TV and radio distribution over the internet. It was done in the 80s already. People thought of transmitting TV and radio over the internet, but people did not think that YouTube would come. So when you distribute TV, in fact, you don't use multicast because everybody's watching a different thing. So unicast is used primarily. It is used in industrial engineering, in industrial computer networking, where it's very useful to be able to send to a machine without knowing which machine it is. And sometimes, perhaps several machines are receiving the data. So typically sensors that send information to somebody who's supposed to receive them, that information may be received by one machine that will propagate and do number crunching, but it may also be used, for example, by a network management application or a system management application, in smart grid, a SCADA, that observes everything, does not act on it, but just keeps a log to see if things are working well. So that is useful, I would say, for embedded computers. The IPv4 packet contains 20 bytes of header. Most of it, I mean, not most, but 40% of it is the source and destination address, 4 bytes each. And then there are 3 more bytes that contain a number of things that we will discuss in detail. The most important thing is the protocol. Protocol means what is included inside the IP payload. We have seen 2 possibilities, UDP or TCP. Now, when you receive an IP packet, there is no way to know whether it's TCP or UDP other than if IP tells you what's inside. Because what's inside is bits. So you receive a string of bits. Is this bit an a TCP segment or a UDP datagram? You don't know. If you know it, you can analyze the content, but if you don't know it, it's just binary random thing. So this has to be indicated by the layer below. It's a general principle, which is not always true, like all principles, but generally it's the responsibility of the layer below to indicate what is the nature of the layer above. And where in the physical layer, you need special mechanisms, pilot tones, similar things to know what is, for example, the encoding scheme. Another important field that is contained in the IP header is the time to live that we will discuss a bit later, and a number of other fields called total length identification fragment offset that are used for fragmentation, which is a very specialized topic that we will see a bit later, that we can ignore for the time being. We have seen that there are IPv4 packets, but also IPv6. I recall that they are incompatible. If I send you an IPv4 packet and you expect an IPv6 packet, things won't work. So the MAC layer has to indicate whether it's an IPv4 or IPv6 packet. IPv6 otherwise is the same as IPv4, but is using different addresses. In practice, they are completely incompatible. So if I have a web browser, if you have a modern web browser, or not even modern, if you don't have an extremely old machine, it runs both IPv4 and IPv6. TCP, there is no TCP-V4 and TCP-V6. TCP is the same, the MAC layer is the same, it's only the IP layer that's different. But that's sufficient to create a lot of chaos, because only the IP layer being different means all the software is different. If I have an application program that is designed for IPv4, an old program, in this program there must be IPv4 addresses somewhere. This software somehow has to use DNS to find what's the IP address, bind the IP address to a socket, etc. Those things are in principle invisible to the user, but they are present in the program. So the code has to be IPv6 or IPv4 compatible. But the protocols themselves, TCP, and even the application layer protocols are independent, but the code themselves are not. Routers also have to do the two differently, so we can imagine a router as being a double machine that routes IPv4 packets and IPv6 packets. We will see in the lab that in many cases, not all, but in many cases, even the processes that are used to do the work of the router are separated, one for IPv4, one for IPv6. And then you may have IPv6 hosts or IPv4 hosts. An IPv6 only host, as is shown here, can talk only to an IPv6 server, or a server that has both IPv4 or IPv6, but it cannot talk to an IPv4 only server. At least it cannot talk directly. We will need to solve the problem, and this creates considerable complication that we will see a bit later. In IPv6, there is the concept of LinkLocal addresses, like there is in IPv4, except in IPv6 it's used systematically. In IPv4, when your machine boots, if there is a machine, a DHCP server or relay to give allocation, to allocate an IPv4 address to this machine, it will have one IPv4 address, and that's the end of the story. With IPv6, for some reasons that are perhaps not entirely obvious, an interface typically has multiple addresses. One of them is a LinkLocal address, an address that is always valid when this interface is alone and does not require any router. And those addresses start with FE80. And it will also have multiple addresses, as we will see later. And to make things even more complicated, the IPv6 routing table, what is in a routing table? In a routing table, there is an information. If I want to go to this prefix, the next hop is this address. But since the next hop is by definition something that is on link with me, that is directly attached to a local area network that is with me, that's the definition of a next hop. Right? Interrupt me if something is not clear. So the next hop is necessarily on link with me, therefore I can communicate with it using a LinkLocal address. Therefore, in the IPv6 routing table, we will see for next hop always only LinkLocal addresses. Now, LinkLocal address is ambiguous. You might have two systems. It doesn't tell you on which interface you have to send it. So you have to manually write somehow the interface, which is given in this case by %1, %2. It means on ETH1, ETH2. This is a thing you will see in the routing table. Depending on the interface we use, Quagga or others, we might see different conventions, but this is something we will often find. Here are IP addresses of EPFL. You see one of the major problems of IPv6, right? On the left you have IPv4, on the right we have IPv6. The addresses are very, very, very long, so it becomes really a pain to write IPv6 addresses. It's a pain to write them, but after all, nobody writes addresses. What we write is queries to Google or URLs, so names of services and computers, not addresses. But if you have to write them, you will have in this course, then they are long. Now they are long, but they are structured. An EPFL public address starts with 2001. This prefix was standardized in 2001, but it's not the number 2001 because it's an hexadecimal number. It's a much larger number, but people will read it as 2001. 620, 618, this is the prefix of EPFL. Now, the difference with previous is that 2001 620 is the prefix of switch, so the internet service provider that serves all Swiss universities, which means that all Swiss universities have something in common, 2001 620. So when a router in the middle of the internet, for example, in the middle of the US, is forwarding a packet to a Swiss university, all it needs is to know how to reach switch. So it has one entry for 2001 620, which is the correct thing to do because we are served by switch and switch connects to the backbone providers. So this is exactly the thing to do. In IPv4, the same router has one entry for ETH, 129, 132, one entry for EPFL, 128, 178. There's nothing in common with those two. 128, 130 is, I don't know which network, but it has nothing to do with Switzerland, or it's not even a university. So we can aggregate more with IPv6. In IPv6, there are also private addresses, but since the prefix, the scale, the size of the address field is much larger, we can have considerably more private addresses. And the first bytes are FD, indicate private addresses. And one beauty of having such long prefixes is that typically, if you have a well-managed network, you can arrange to have the same address for the private address and the public address. So the address of a machine is the concatenation of the red part, which is the prefix that indicates EPFL. Then you have the pink part, 1A6, which is an identifier of a subnet inside EPFL. And then the green part, which is the host part. If you do things well, you can arrange things such that all the variable parts of the addresses, the subnet and the host part, are the same in the private and public domain. Well, why would you care about doing that? Well, if someday your machine that has private addresses need to have a public address, for example, then you can merge them. You don't need to do renumbering, for example. This block of private addresses is one of the several IPFL private address blocks. That's the block that is used for the smart grid. IPv6 addresses are long, so there are some human-readable compression rules that have been standardized. It's important to know them, otherwise you might misunderstand an address. The rules are that you write them by blocks of 16 bits, which means 4 hexadecimal digits. And empty blocks can be omitted, and leading zeros can be omitted. For example, if I look at the first of those addresses, the last block is 0C26. I can omit the 0 as long as I make it clear that there are, with a colon sign, where the block boundaries are. And then we see that in this address, those address 202, etc., those are addresses that are used in the INF 019, in the special network we make available for you in the wireless LAN. There's lots of zeros in it. So it's a pain to write all those zeros. Plus, human beings are unable to write a large number of zeros correctly. You'll write more or fewer. So you just omit them. You put empty block. Of course, this makes sense only if it appears only once. If in the same address you have two empty blocks, you don't know how many zeros there are. So the rules are, you can suppress the zeros, you can suppress the empty blocks, but you can suppress only one empty block in an IPv6 address. Voila, thank you very much, and see you in the lab tomorrow.